Good afternoon, students. In the last class, we discussed the topic that is extrinsic semiconductors, right? So, in extrinsic semiconductors, we have two types. So, one is N-type semiconductor, and another one is P-type semiconductor, right? So, what are extrinsic semiconductor means? We are adding impurities to the pure semiconductor, then those devices or then those materials we call as extrinsic semiconductors, right? So in N-type semiconductor and P-type semiconductor are the types of extrinsic semiconductors. So here in these two cases also we are adding the impurities. So in N-type semiconductor we added pentavalent impurity, and in P-type we are added trivalent impurities, right? So the purpose of adding the impurities to the intrinsic semiconductor, so intrinsic semiconductor is nothing but the pure semiconductor, right? That is the purpose of to increase the conduction. That means to increases the number of charge carriers. Right? So here the purpose of adding the impurities is to increase the number of charge carriers. So we have two types, that is N-type and P-type. So in N-type we increase the number of charge carriers, that is electrons. So electrons is negatively charged particle. So in by adding pentavalent impurity in N-type semiconductor, the number of charges which are increased is electrons. So these are called as majority charge carriers. That is majority carriers, that is electrons. Similarly, in trivalent impurities, the number of charge carriers again it increases, but here the number of charge carriers are increased, or that is holes. So these are we call as positively charged carriers, right? So in the last class we discussed up to this one, right? So next, as the number of charge carrier increases and we are adding the impurities to the pure semiconductor, the energy bands gets altered because of we are adding the impurities. So what happens to the energy bands in N-type semiconductor and in P-type semiconductor, right? So the energy bands, we have the energy levels. So this one is the conduction band, sorry, valence band, and here we have conduction band, right? So this one we call as valence band, here we have conduction band. So as energy bands get altered due to the adding of impurities, so we have almost the number of electrons, that is in valence band we have completely filled electrons, right? So for that we have the energy level we call as EB, right? So similarly in the conduction band almost it is empty filled, so here the energy of the conduction band we call that one as EC, right? So this in direction, this one is the electron energy levels, right? So after adding the impurities, so first we discuss the in N-type semiconductor we have, that is N-type semiconductor we also call as donor semiconductors, right? So in P-type semiconductor we call this one as acceptor, right? Because it's giving the electrons to the semiconductor, it is giving the holes to the semiconductor, that means it taken the electrons from the pure semiconductor, right? So that means one more extra energy level is formed in N-type semiconductor, so that one energy level is the donor energy level, so that is slightly below the energy level of the conduction band, so that one we call as ED, right? So this one we can written in capital, that is ED. As we know, in conduction, that is in valence band, the electrons are completely filled for a light, that is for a room temperature or for very slow temperature. The electrons which are present in this conduction band, because in n-type semiconductor we have excess number of the electrons, right? So these electrons are get accumulated into that of the valence, that is donor band, that is here we have the number of electrons, right? So at room temperature, for the very less energy, that is of 0.01 electron volt, so these electrons are shifted to the conduction band here. So these are the electrons which are shifted into the conduction band, leaving the holes in the valence band, because in n-type semiconductor, so this is we are studying in n-type, right? So n-type semiconductor, we have one extra energy band, so that band is the donor band, that is we call it that one as energy level ED. So as the valence band has several number, that is more number of the electrons, because in n-type semiconductor we have excess number of the electrons. So these electrons are accumulated in this energy level. So the extra energy level is slightly below the conduction band. So as all these electrons are present in the ED, right? So for very low temperature, that is or at room temperature, of the energy is how much? That is nearly 0.01 electron volt. These electrons which are present in this energy level is accumulated into the conduction band, and which is responsible for the conduction of the electrons, right? So the energy band get altered. So one more energy level is formed just below the conduction band, so that band we call as donor band, that is represented by ED, the energy level of the donor band, that is just below the conduction band, right? For a slow temperature or for a room temperature, the electrons are easily jumps to the energy levels in the conduction band, right? So this is in case of n-type semiconductor. So if we observe in p-type semiconductor, so this one is the valence band. Here we have the conduction band, right? So in valence band, so this energy level is EC and here energy level is EV, right? So what happens in p-type semiconductor? So in p-type semiconductor, the majority charge carriers are the holes. That means the maximum number of the holes which are present in the valence band, right? So for that purpose, one more extra energy level is formed just above the valence band. So that one we call as acceptor band. So that one energy level we call as EA, right? So this energy level is just formed above the valence band. That means this valence band has maximum number of the holes, right? So for a very low energy, that is at room temperature, approximately 0.01 to 0.05 electron volt, right? So what happens in this energy? These holes are get excited to the band, that is acceptor band. So as it gets excited here, that is the holes which are present in this energy level, right? So for this energy, these holes are just falls down to the energy levels, because here there is a empty space. That means as it shifts to here, the electrons which are present in the valence band is shifts into the conduction band, right? So for that purpose, here the electrons are present. So this is in p-type. So p-type, the energy level is formed just above the valence band, right? So here what happens for a low energy at room temperature, the holes which are present in the energy level, that is EA, that is acceptor, it gets ionized and it falls into the energy levels. So as it falls to the energy levels, the electrons which are present in this valence band are get ionized and it jumps to the conduction band, and here it responsible for the conduction, right? So this is in n-type and p-type semiconductor, right? So the net charge carriers in these bands can be given as at equilibrium Ni equals to, that is Ni square is equals to Ne into Nh. So that is when at equilibrium. So at equilibrium, where Ni is called as number of charge carriers. So Ni is the number of charge carriers and Ne is the number of electrons and Nh is the number of the holes, right? So these will helpful in further studies, right? So two extra bands are formed, that is when added impurities to the pure semiconductor. So one is donor band and another one is acceptor band. So those energies we call as Ed and Ea, right? This is about the energy bands in case of n-type semiconductor and p-type semiconductor. So the most important is about this one. In electrons are the majority charge carriers and in p-type the majority charge carriers are the holes, right? So the next topic is PN junction. So in the name itself, it is the combination of p-type and n-type semiconductor. So what is the helpful to study this one? That is the PN junction, right? So PN junction is the basic building block of the semiconductor devices. So PN junction is the basic building block. That means it is the basic phenomenon we call, right? So basic building block to study the semiconductor devices such as diodes and transistors, right? So the chapter is about the semiconductor. So until now we discussed about what is semiconductor and types of semiconductor. So the next step is here to study the semiconductor device. We need to understand. So what is PN junction, right? So this will helpful to explaining the diodes and transistors, right? So that is how PN junction is formed and how PN junction works when external voltage is applied. So in this topic, we are going to study these two. That means how PN junction is formed and how PN junction works when external voltage is applied. So these are the main concepts in the topic, that is PN junction. So starts with the PN junction formed. That means the formation of PN junction. Right. So for that, the explanation, that is study about the formation of PN junction. For that, first considering a silicon wafer, that means a thin slice of the silicon semiconductor. So silicon is the semiconductor, right? So here we have the thin silicon wafer. Right. So initially it is a intrinsic semiconductor. Now this silicon wafer is coated with small amount of pentavalent impurities. Right. So initially we are taken one silicon wafer, that means wafer is nothing but thin slice of the intrinsic semiconductor. So that pure semiconductor is again coated with the pentavalent impurities, right? So now what happens here, as this is coated with the pentavalent impurities, so some part of this intrinsic semiconductor, that is p-type semiconductor, is converted into n-type semiconductor, right? So forming the two regions, so one is p region and another one is n region, right? So first what we did means considering one silicon intrinsic semiconductor, next we coated with the small amount of the pentavalent impurities, then it becomes extrinsic semiconductor, right? Because as we coated with the pentavalent impurities, right? So next, some part of the p-type silicon is converted into the n-type silicon semiconductor, forming the two regions, that is one is p region and another one is the n region, right? So as of we studied the n-type semiconductor, the majority charge carriers is electrons. That means the electron concentration is more than holes. So this is in n-type, right? So this is we studied in n-type semiconductor, the electron concentration is more. Concentration is nothing but number of electrons per unit volume, right? So this can also we can note. The concentration is nothing but number of electrons. So electrons is denoted by E, its power is minus, right? So number of electrons per unit volume. So that one we call as concentration, right? So next, in p-type, so in p-type semiconductor, that means holes or hole concentration is more than electron, right? So here hole concentration is nothing but number of holes per unit volume is more. That means here we have hole, that is denoted by O, or we can write this one as H, right? So up to this, as we studied in the previous classes, that means in n-type semiconductor, electrons are the majority charge carriers, and in p-type semiconductor, holes are the majority charge carriers. So here we have a certain volume, then concentration of the electrons per unit volume is more. That means in N type the electron concentration is more, and in P type the whole concentration is more, right? So while formation of the PN junction, we are going to study the two main processes, right? So we need to understand two main processes. So in that first process is diffusion, right? So this one, the meaning is same as you already studied this one in the biology, the term diffusion. So next, the process is drift. So we need to understand these two processes while formation of the PN junction, right? The first process is diffusion and the second process is drift. So diffusion, as in N-type semiconductor, the electron gradient is nothing but the number of electrons with respect to its length, right? So for example, in this length we have 10 electrons, that length is 2 meter, then we call this one as electron gradient, that is equals to number of electrons divided by its length, that becomes 5, right? So electron gradient is always up, in the terms of gradient is nothing but divided by the distance x. So if it is electron, then it becomes E divided by x, right? This is similar to that of the rate of change. So as the term which we are going to use rate, so wherever we are using rate, so always it is divided with respect to time. So similarly, as we are using the gradient, always we are going to divide with respect to the distance, that is either length, either height, right? So here we have up to this much length. So here both sides we have the same length. That means the gradient of the electrons is equals to the gradient of the holes. Both are same. So if we consider up to here, we have 10 electrons. Then for this distance is 1 centimeter. So similarly here, this distance for 1 centimeter, again we have 10 holes, right? That is nothing but the gradient, number of the electrons which are present in that length. So if we consider here 2 meter, then number of electrons which are present in this 2 meter, we call that one as electron gradient. Similarly here, the whole gradient, right? So here in both the cases, the gradient is same. So next, what happens? So in N type we have more number of the electrons, and in P type more number of the holes are present. That means the electrons which are present are free electrons. So what happens? The electrons which are present in N type will diffuse into the P type, right? So we have to recall the P type semiconductor and N type semiconductor. So in N type semiconductor we have always one extra electron. This is because we added the impurity, right? So because in N type we have always 5 electrons, so in P type we have always only the 3 electron, right? So here it is acts as an acceptor, so hence the electrons which are present in N type will easily diffuse into the P type, right? So as it diffuses from N to P, that is the electrons which are present in N type semiconductor will diffuse into the P type semiconductor, and similarly the holes which are present in P type semiconductor will diffuse into N type semiconductor, right? That means the transfer of electrons from N to P and holes from P to N, right? So the next point, if we written here, due to electron gradient, electrons from n-type silicon semiconductor is diffused into p-type silicon semiconductor, right? The diffusion of the electrons from n-type to p-type. So that can be written like this. That is the electrons diffusing from n to p. So similarly, due to hole gradient, hole holes from p-type silicon semiconductor is diffused into n-type silicon semiconductor, that is from P to N. Either we can directly written as holes which is diffuses from p-type to n-type, and the electrons diffuses from n-type to p-type, right? So the process of diffusion of the electrons from n-type to p-type and the process of diffusion of from holes from p-type to n-type. So these electrons and holes combined we call as, so these two combined what we call as charge carriers, right? So these two we togetherly we call as charge carriers. That means the electrons which diffuses from n to p and holes which diffuses from p to n. That means the diffusion of the charge carriers from electrons flowing per unit time, that is E divided by T. So here observe here the electrons are flowing from left to right. The direction of the flow of diffusion current is from, sorry, the electrons is flowing from right to left. So the diffusion current is the direction from right to left. So this one is the diffusion current, right? So this is about this process, that is diffusion. In the first process, we observe the highly number of, that is more number of the electrons which are present in n type and holes are present in p type. These are get diffuses from one region to the another region. So as electrons which is traveling from n type to p type, so the direction of the current is from n type to p type. So that current we call as diffusion current, right? So next point, so next what happens as the electrons which are moving from n type to p type, so here electrons are moving nothing but keeps remaining here the positive charges, right? So leaving the positive charges here as electron moves. So if one electron is moving, then it leaves the ionized atom, or we call this one as ionized donor, because these are the donor atoms. As electrons moving, it keeps leaving the positive ions, that means ionized donor here, right? So these are not able to move, so that means these ionized donors are immobile. So mobile is nothing but moving from one place to another place. So these are the electrons which are free electrons. That's why these are moving from one region to another region, right? So these donor ionized atoms are immobile. So that means these are not able to move from one place to another place. That is one region to another region. That is because these atoms are bonded with neighbor atoms. The reason is what? These ionized atoms are bonded with the neighbor atoms. So as the number of electrons are moving from N to P. We have one electron moving means one ionized atom. So 2 means 2, 3 means 3, 4 means 4. So as how many number of the electrons are going to diffuse, so that number of the ionized donor atoms will remains in the N type, forming a layer, right? So these are immobile, so that's why these are forming the layers on the side of the N type semiconductor, right? So I will remove this. So this is P type, this is N type. Here we have holes, here we have electrons, right? So as the electrons are drifting from here, so writing here electrons and here writing holes. So leaving and forming the positive donor atoms as a layer like this, right? So if many number of electrons are diffused, then that much number of the donor atoms forming the layer, right? So similarly, here in P type, holes are diffusers from P type to N type, leaving the acceptor. So here we have ionized acceptor or acceptor atoms, right? So leaving negatively charged on the region, and they also form the layers, right? So here they form the layers of negatively charged. As how many number of holes are diffusers, so that number of the electron layers is formed like this, right? So this one is called the layer of both the sides of P and N type. This space region formed by the charges, so this region we call as depletion region, right? So this region we call as depletion, right? So as in this region is formed both the negatively charged and also positively charged, there is a formation of electric field. So due to negatively charged and positively charged atoms which are formed here in the depletion region, so due to negatively and positively charges, there is a formation of the electric field. So due to this formation, that is formation of the electric field from positive charge to negative charge. So there is a formation of electric field because here these two are ionized charges, that is positive charge and also the negative charge. So the electric field, in which direction it is? So the electric field direction is, that is from positive to, that is positive charge to the negative charge. So due to this electric field, right? So next what happens? Due to this electric field, the electrons which are present in the P side will move into the N side region. So in the depletion region, right? So due to this electric field, so electrons are drifted to the N type and holes are drifted to the P type, right? That means the electrons which are present in the p type will move into the n type region like this. So similarly, in the positive charge which are present in n type will diffuse, that is drift into p type. So here also what happens, there is a motion of the charge carriers, that is from p type to n type within the depletion region, that is due to the electric field. That means due to the external force, these electrons are moving from p type region to n type region and n type region to p type region. So that process we call as drift. The process we call as drift. So the first process is the freely electrons are easily diffused from n type to p type and holes from p type to n type without any force. So here we are not applied any force to these electrons. These are easily diffused from both the regions, right? So what happens in the depletion region means the electric field which is formed due to these positively and negatively charges, the electric field is from positive charge to the negative charge. So electric field is nothing but the force. So electric field we have Q into F. That means due to this electric field, the force, due to this force, the electrons are drifted from p type to n type and the holes are drifted from n type to p type. That means the positive charges are drifted from n type and negative charges are drifted from p type, right? So that process also the charges are drifted and the flow of the charges we call as current. So that current we call as drift current. So because here also the charges are moving. So as charges are moving is nothing but there is a flow of current. So that current we call as drift current. So this drift current is always opposite to that of the diffusion current. So observe here the electrons which are drifting means moving from p type to n type, that is from left side to right side. So as electrons moving from left side to right side, so that current we call as drift current. Now observe here, the drift current is from left to right and diffusion current is right to left. So that one is also one point, right? So in PN junction, drift current is always opposite to that of the diffusion current. So next point, so if you understand this concept clearly, then only you can understand the working of the diodes and transistor. So as of your syllabus, the transistor is completely removed. So that one is the lengthy topic, right? So the next point here is drift current is always opposite to diffusion current, right? So as we are discussing about the current, one is drift current and another one is the diffusion current, right? So in initial states, the formation of the depletion layer is very less compared to that of the availability of the electrons in the n-type and p-type semiconductor. So what it indicates means, so in initial state, the diffusion current is more than that of the drift current, right? So initial state diffusion current is more than drift current, right? So as of initial state, we observe here only two layers of the electrons and two layers of the positive charges are formed, because we have only this much of the electrons are diffused. As time passes, the number of the electrons diffusion goes on increasing, and also the number of the holes which are diffusion is goes on increasing. That means the layers of form is more. That means as time passes, that is as the diffusion increases, right? As diffusion increases, the formation of the depletion layer is also increases. Now observe here. Like this. So as diffusion, here the number of electrons which are diffused and holes which are diffused. Now if you observe here, the depletion layer form is more. So as the depletion layer is more, the flow, that is the drifting of the electrons is more. So as the drifting of electrons is more is nothing but the drift current is more than that of the diffusion current. Right? So as diffusion increases, depletion layer, that is formation of depletion layer also, formation of depletion layer also increases. So as these two increases, drift current is more than diffusion current, right? So that one is the next point. So as it reaches equilibrium, at equilibrium, so equilibrium nothing but the total number of the electrons, free electrons which are diffused into the p type and number of into the n type. So from this the complete formation of which layer, that is depletion layer. So here we have like this, right? So that is from this we observe that the diffusion current is equals to the drift current. So at equilibrium, the net current in the junction is, hence we form, that is the formation of PN junction. So this is how the PN junction is formed. So this is how we form the PN junction. Finally, the net current across this junction, we call that one is 0, and hence that one is the PN junction. So this is the of the PN junction. So during the formation of PN junction, first, so the key points we need to remember the formation of the PN junction is, the first is we are taken a wafer of the semiconductor, right? So as this wafer is added with pentavalent impurities. So here the two processes will take place. One is diffusion. So the flow of charges through the diffusion, the current we call as diffusion current, and the electric field is formed. So due to the electric field, the charge drifted, that is forcible moving of the charge. That one we call as drifted, freely moving of the charges, that process we call as diffusion. So there is diffusion and drift. So drift is due to the applied force, that is due to the electric force. That force is given by the electric force, that is because of the negatively and positively charges, right? So the current which is flowing in that electrons, drift current. So at equilibrium, the drift current is equals to diffusion current, and hence the net current is 0. Likewise, the formation of the P junction is formed, right? So in the next class, we will discuss how the PN junction will work when this junction is applied with the external voltage. That means when we connect this junction to the external source, that means voltage. If we connected this semiconductor, that is this, to the outside battery, so how it will work, right? So that will be discussed in next class, right? Thank you. Doubts?